Welcome everyone. What H minimizes the true risk? For the above scenario. So by above scenario I mean we have a binary classification problem and the loss function is a 0 1 loss function. So for that particular case what hypothesis minimizes the true risk? Okay. So to give you the answer is consider a hypothesis, and by the way one can use the name of classifiers and regressors for this hypothesis as well. So this hypothesis function is what is called as a classifier, isn't it? If y is discrete, if y is continuous, this is what the regressor is. This is what your classifier or regressor is. Okay. So consider a hypothesis function or a classifier in this case because we are looking at a binary classification problem defined as follows. So let's call that hb of x. This is equal to, this is the definition of this function, this is equal to class 0 if the posterior of y equal to 0 given x is greater than posterior of y equal to 1 given x. It chooses the other class, otherwise I will also write that maybe if posterior of y equal to 1 given x is greater than or equal to, so I am breaking the tie arbitrarily, there is no sanctity to this, which one should I have to use, the tie is broken arbitrarily. So this is how I choose. So I define a classifier or a hypothesis that would assign class 0 if the posterior of y equal to 0 given that particular x is larger than posterior of y equal to 1 given x and the other class otherwise. So it just looks at the posterior of y, evaluates it for both the classes, and it chooses the class based on which one is higher. Seems like a rational thing to do, right? So if you have access to computing this, by the way, we are assuming that we have access to all distributions that we need and we have a way to compute this is what we have assumed, correct? So if I have access to compute this, I can define a classifier this way where I decide based on the class posteriors. Is that okay? Now this classifier is what is known as the Bayes classifier, named after the famous statistician Bayes. It is called the Bayes classifier. The claim is risk associated with the Bayes classifier is always less than any other classifier for all classifiers that you can consider, which means that this is the optimal classifier. If you are solving a binary classification problem, then you cannot do better than Bayes classifier in terms of minimizing the risk. See, this result, okay, is general enough for a large class of problems, but I will prove that for the case of binary classification problem with 0 1 loss because that is the easiest. Okay. Similar results can be proved for regression problems and they can be proved for k class classification problems and so on. Okay, we will see that. I'll state some of those results without proof, but this one we will see. Is this statement clear? That the question that we asked is what H minimizes the true risk for the above scenario, and the answer is the one that decides this way, which is called the Bayes classifier. This function minimizes the true risk is the claim. So let us prove that claim. Yeah.
We came up with this function and now we are claiming that particular last limit, right? Like we didn't derive this hypothesis function from somewhere.
Can do that as well. Okay. The question is, how did Bayes come up with this and then show that it is the least, it's a classifier with least risk? Can't you do the other way around? meaning start from the definition of risk, okay, and deduce that this is the classifier that minimizes the risk. Can be done, it's algebra, I will show you that. Okay, when we walked through the proof, we will see that you can start from the definition of risk and derive this result as well.
For any dimensional problem, any kind of problem.
Yes, you can. Okay, I mean you have to do a bit of variational calculus and function approximation, function analysis to do this, because see, look at this, no, this optimization that we solve, right, the problem of risk minimization, the true risk minimization, this is an optimization over functional function spaces. See, we know how to differentiate with respect to variables, right? We have learned calculus. Do we know how to differentiate with respect to functions? I mean, mathematicians do, it's called variational calculus. We can differentiate with respect to functions. So you need a bit of variational calculus to derive some of these results, because see, this is an integral, as we will see, because it's an expectation. So typically if you are looking at continuous random variables, the risk becomes an integral in some high dimensional space. So, and that involves this hypothesis. So what you are actually looking at is the derivative of an integral with respect to a function. Get it? We don't know how to do it, at least people who have studied high school calculus or undergrad calculus don't know it unless you have actually studied variational calculus, that you need to differentiate integrals with respect to functions. Okay, that is why I do not take that route. The way it is generally shown is that you assume that you know the result and then show that this is correct. Okay. Any other question? Okay, let us show that now. Okay, proof. It's a cute little proof, so let's do that. Let ace I of h denote all x in RD such that my classifier assigns class I to it. So I is either 0 or 1. Did you get the notation? What am I doing is I am taking RD, which has all my data. I partition this RD into two non-overlapping sets. Okay, I will also write that is 0 of h does not intersect with h1 of s1 of h, and the union of these two is RD. So what is this? What is this set, by the way? This set is set of all data points in RD that gets labeled as class 1 under the classifier H. So you take a classifier and see what all points in RD are being classified as class 1, that is S1 of H. So you take all points that are being classified as class 0 under this classifier H, that are S0 of H. Come again? Here, na? This should be 0. Okay? Come again? Subset of RD, right? Yeah, correct. Yeah, union will be, yeah, we'll say it is in RD. Okay, intersection is null. Okay, so this is how I partition RD into 2 points. Now, so this is for every H. So you take any H in the hypothesis set, you can partition RD into these two partitions, right? Okay. Okay, come again.
So I think it has to be X, all the examples of X, right? If you put a subset case, even one example can satisfy this condition.
Okay, see, the question is, suppose you take everything in the distribution, then it is RD. So if you only take samples from the data set, then it is a subset of RD. It depends on how do you want to see it. Okay, because we are considering the true risk, It's okay if we say that we consider all points in RD. That's the only difference. Okay. Or if you take data set, then there are some points that are never considered because they are not in your data set. That's it. Let's take the entire distribution because we are not looking at empirical risk here, we are looking at true risk. It's okay, no? Okay. Now, see, one other side note is, do I need that result now? I don't, but anyway, I'll note that risk for this particular case is the probability of the indicator that h of x is not equal to y. Why? It's because of the following. Let me just, we will actually use this result in a different way. So what is the risk for this particular case with 0 1 loss for a binary classification problem? It is the expectation of the loss function under the Shannon distribution. Okay. Now this loss function is an indicator random variable. Why? Because it can take two values, right, with certain probabilities. So what is the expectation of an indicator random variable? It is the probability that it takes one of the values. That's it. So that's why the risk is equal to the probability. See, we have defined the risk as 1. So if you look at risk as an indicator random variable, then that risk, the loss function as an indicator random variable, loss function takes value 1, it's a Bernoulli random variable, it takes value 1 if the hypothesis is not matching with the true label, correct? And that's why it's the probability of this this particular thing. Anyway, it's a side note. So which is equal to the probability of the indicator that this is, write it here, where I is an indicator random variable, Bernoulli random variable. That's simply algebra, right? This is what it is. So let's write that. So what is this equal to? This probability can be split into, so this event, right, the event of h of x not being equal to y can happen in two ways. One, when the true class is 1 and the classifier predicts it as 0, and the other way. Okay, let's write that. This is equal to the probability of h of x predicting y and y equal to 0 plus the probability of h of x is 0 and y equal to 1. Why could you add these two probabilities? They are disjoint. Okay. Now this is equal to the probability of x being in S1 of h and y being equal to 0 plus x being in S0 and y equal to 1, because that is how we have defined these two sets, correct? Now this is equal to, this is a joint distribution. I will write the joint distribution as a product of marginal and conditional, equal to p probability of y being equal to 0 times the conditional distribution of x given y, as x is in S1 of h given y equal to 0, right, plus conditional distribution. Actually, yeah, so when I condition, this is x is in S0 of h given y equal to 1. Is this clear? This is simply using the definition that the joint is equal to the product of marginal and conditionals. That's it. Is this clear? I will be writing this. So now this is equal to probability of y equal to 0. What is this? What is, see, we have taken x to be in RD as a continuous random variable, right? So now if you want to, actually this is not equal, I will have to write p because this is a probability that I am looking at. Okay, I will have to compute that probability. So you have to compute this probability for a continuous random variable. What do I do? See, if I have to compute the probability of a particular random variable being in a set, how do I compute it for a conditional random variable? Integrate the PDF. We'll have to integrate the PDF. So let's do that. So this is the integral of the PDF y equal to 0 dx plus so I have to write this as this because whenever I write a conditional distribution, right, it's always that the conditioning random variable is fixed at a particular point, right? This is what it is. And this integral is over what set? This is over S1 of h and this is over S0 of h. And note that these two are two different distributions, two different conditionals, okay, by definition. This is what it is, right? Okay, now look at this integral. Now we know, see, we are computing the sum of two integrals, okay, and integrating these two integrals over two disjoint sets, okay. Now for each x in RD, when you compute this true risk, only one of these two integrals will get integrated, no, will be considered. Why is that? Every x will either belong to S1 or to S0, therefore when you compute this entire risk, for each x, either of them will get evaluated, correct? So let me write that. Since S1 of h does not intersect with S0 of h, for every x in RD, you only consider one of the two integrals. So we are computing this risk, right? Now we are integrating this over S1 and we are integrating this over S0, right? What is integral? I mean, you can look into that roughly as taking all points in x and computing this and adding them, correct? Infinitesimal. So let's take an x in RD. So if you want to compute the risk associated with it, you will either evaluate this integral or this integral depending upon what that classifier does on that particular point. You cannot compute, you cannot take both the terms, correct? That's what I am saying, because S1 of h and S0 of h does not intersect with each other. Is this clear to all of you? Because this is the crux of the proof. There is only one step that remains now, okay. Now can somebody tell me amongst these two integrals which would be computed at each x? Did you understand the question? So you all agree that for each x one of the two will be evaluated, right? Which one will be evaluated for each x? Depends on h. Depends on h. Okay. Now if h chooses S1, then the first integral will be evaluated. If it chooses S0, then the second integral will be evaluated. That's it. Depending upon what your h does. Now this is, so far this is same for any hypothesis. Now, for the particular case of Bayes classifier, now look at this integral and tell me which one would be chosen in the case of Bayes integral. So let me write this thing, so that it is clear. So this R of h is given by the integral of P of y equal to 0 times, sorry, it's the density, right? P x given y equal to 0 plus okay, this is what we have, right? This is the risk now. Now for the case of Bayes classifier, which of the two integrals will get evaluated? So this is over S1, is it? This is over S1, this is over S0, correct? Now for Bayes classifier, which one will get evaluated? No. No, it depends upon what the true class is, no? See, remember what Bayes classifier is. Bayes classifier always chooses based on the posterior. It chooses based on posterior. Whichever posterior is the highest, it will choose that particular class. If that is done, then which one of these two integrals will be evaluated at each x for the Bayes classifier? Just think about it for 30 seconds, I will tell you the answer. Did you get the question? The question is, so I will just write down, no, HB chooses or HB is equal to 1 if y equal to 1 given x is greater than if I want, I can extend this. This implies what is P of y given 1 y equal to 1 given x, use Bayes law, is equal to x given y equal to 1 times P of now tell me which of these two terms will be evaluated for this particular classifier. Oh, what do you mean by right side? For what case? If the true class is 1, then which one will get evaluated? Depends on what Bayes classifier does. Okay, the question that I am asking is that, okay, so let me just tell you the answer. So always for the Bayes classifier, the term that is the least of these two will get evaluated. Why is that? What is S1? S1 are those cases for which the Bayes classifier or any classifier chooses class 1. When does Bayes classifier choose class 1? When this product is greater than this other product. And whatever is within the integral over the set of S1 is the one that is minimum of these two, isn't it? Shall I repeat? This is the key point. What is S1? S1 is the set, okay, of all x's on for which classifier says 1. When does Bayes classifier say 1? Bayes classifier says 1 when this product is greater than this product, which means that whatever is within the integrand when you are considering set S1 is the minimum of these two. Do you see that? And the same thing can be said for the other class as well. When does the Bayes classifier choose S0? It chooses S0, let us write that, right? Chooses S0 if P of x given y equal to 0 times P of y equal to 0 is greater than P of x given y equal to 1 times P of y equal to 1, isn't it? Which implies R of HB is equal to, you take the integral over all RD, what do you take? You consider the minimum of does all of you see this argument? Are we done with the proof? Are we done with the proof? So we are, because these two terms are non-negative because they are either probabilities or density function being evaluated at a point which is non-negative always. So if you are integrating functions that are non-negative and at all points, if you choose in such a way that you always take the minimum out of two quantities, then it should be the minimum amongst all possible choices of h, isn't it? That's it. Therefore, okay. So this result says that one cannot do better than a Bayes classifier, no matter what, in terms of minimizing the risk. So if you choose your classes based on the posterior of the labels given data and you choose to make the class to be the one that has the maximum posterior, then you achieve the least possible risk. Okay. It says that you cannot design a classifier that is better than a Bayes classifier. Now this is a theoretical result, okay, but what is the problem here in practice? Can you build a Bayes classifier? You can't. Why? You don't know the distributions. Now it boils down into a distribution estimation problem. So to build a Bayes classifier, you need to estimate these distributions. So now, given some data, you can cast the problem of ML as that of building a Bayes classifier, and to build a Bayes classifier you need to solve the problem of maximum likelihood estimation because you need distributions. You get it? Now the other way to look at it is as follows, right? You remember that when I was discussing maximum likelihood estimation, I told you that we are interested in obtaining P of y given x. What's the reason? The reason is this, that we are interested in building a Bayes classifier and we estimate the posterior of y given x. Okay. So now this result is for the case where the loss function is 0 1 loss and the problem is that of binary classification. Okay. Can I extend this result? Turns out that you can. I will give you one case where instead of solving a binary classification problem, suppose you are solving a generalized classification problem with k classes. Got it? So in this case, what should be the Bayes classifier look like? So there are k possible classes, which means that you can compute the posterior of, when you compute posterior of y given x, it will be a k dimensional discrete random variable that can take values 1 to k with probabilities p1 to pk or whatever, right? There are k path probabilities. Bayes classifier is the one that assigns that particular class which has the highest posterior amongst all possible classes. Just like we did it for the case of the binary classification, you extend that for k class classification. It can be shown using the same argument that the best classifier in terms of achieving the minimum risk when you use 0 1 loss function is a Bayes classifier for the case of k class classification as well. Please take it as a homework and do it. Did you get it? Similar argument, you can just use the same argument here. Okay, that is one result. Are you telling me how to solve it? Try it out. So you write it down. I have told what the classifier is. Write down the algebra and see if you can do it. It's pretty straightforward, given this. Okay? Try it out once. Now the question is, how does this extend to regression problems? Do you understand? Suppose instead of having a classification problem, suppose I use regression problem. Okay, and so note that the true minimizer of the risk, the minimizer of the true risk depends upon the choice of loss function as well. Correct? Now suppose we choose our loss function to the loss function as the squared error loss, and we take up the problem of regression where y is in R or Rk. Can you guess what would be the optimal risk minimizer? Just a guess. No, it's a function. It should be a function of x. No, see, this Bayes classifier is a function of x. H, the hypothesis, the optimal minimizer of the risk, has to be a function of x. Huh? Exactly. It will be the conditional expectation of y given x. I'll start the next class by writing that result. You understood? Suppose I choose my loss function to be squared error, and the problem that I am solving is that of regression. Then the optimizer of the true risk will be the conditional expectation of y given x. I think you might have done this in your stoma, right? This was a result that was shown in the first course of probability theory. If you don't recall it, go back and look at your books. Okay. So what am I saying is, this is the minimizer of the expected So this is a standard problem in probability theory, right? You can show that if you can actually show this, okay, so that this minimizer is equal to this conditional expectation. Okay, anyway, so maybe let it be there.
Sir, are these results also dependent on the loss?
Very much, no? Very much. I told you. So this result is very much dependent on loss function. So now, again, other question that is taken in statistical learning theory is, suppose you choose a loss function, okay, what is the optimal Bayes classifier, or what is the optimal risk minimizer? Sometimes you can analytically find that out, sometimes you can't. But why did we do all this? So what is the reason behind doing all this is that, again, summarizing this particular class. So what did we show is that we looked at the method of empirical risk minimization as the problem of machine learning, where you are given data, define a loss function, compute the expected loss over the distribution, and you can't solve that, minimize the true risk. You take an empirical version of it and then minimize that. So that's your hypothesis or the classifier or regressor. Now one central question is, when and how would the minimizer of the empirical risk converge to the minimizer of the true risk? Okay, most times this question may or may not be answered, but we saw equivalence between empirical risk minimization and distribution estimation. Okay, so continuing that, I also showed that for the case of 0-1 loss function and binary classification or k-class classification problems, the minimizer of the true risk is the conditional distribution of labels given data. So why was this result even proved? I mean, and this particular classifier that chooses based on the posterior of labels given data is called the Bayes classifier, and no other classifier can do better than the Bayes classifier. Now, why did we do that? Is to again reinforce the connection between the distribution estimation framework and empirical risk minimization framework, because the next question that we will be asking in the coming classes is, how do we realize a Bayes classifier? So what do we mean by that? How do you build a Bayes classifier given data? To build a Bayes classifier, we need the conditional distribution to be estimated. Now that becomes a distribution estimation problem. So either you can directly estimate the posterior distribution, right, using some model, or you can estimate what happens is, you can directly estimate P of y given x, or you estimate P of x given y and P of y and combine them to create a classifier. So for the next few classes, we will look at a few methods, okay, or algorithmic methods to estimate a distribution given data. We have already told you that a maximum likelihood estimation is one way to do it, okay. So for a few particular cases of the assumed underlying density, this optimization problem that we solve in maximum likelihood estimation is not tractable. In a sense, what am I saying is that suppose you take your p theta to be this class of density functions called mixture densities, you cannot differentiate that and put it to 0 and find out the optimal parameters. You need to resort to numerical methods to solve it. There is an algorithm called expectation maximization algorithm, or EM. So we will look at that EM, and we will also look at class of methods called map estimators. where you assume your parameters also to be a random variables and you compute posteriors on top of it. So, next set of lectures will be on estimation theory. We will specifically look at the ML estimation that we have already seen and a few examples, and we look at the map estimation and ML estimation for the case of mixture density, which is called the EM algorithm. That is what the next class is going to be. Yeah, so thanks for attending this class. See you in the next time.